In this lecture, we will learn about electric flux. Whenever we have electric charge, then a field exists around the charge. And the field is denoted in terms of electric field lines. From there, we define electric flux. In this lecture, we will talk about electric flux, from where this electric flux came, then significance, and how to calculate electric flux. There are certain factors that affect electric flux. So we will discuss on those factors here and how to calculate electric flux. Electric flux is the rate of flow of electric field through a given area. This is the definition of electric flux. Before understanding this definition, we must know from where it came. Electric field means there must be some charges. So the presence of electric charges represented in terms of electric fields. And to check the strength of electric field, we use a term flux. Now the flux gives the idea of strength of the field, whether it is more or less, where it is more, where it is less. So whenever we want to check the electric flux, generally we choose a test charge and we bring this test charge in the electric field to check the direction of flow and rate of flow. And this is denoted in terms of electric flux. For calculation of electric flux, we assume a surface area from where the field lines pass. As we have discussed in the previous lecture, the electric field is represented by field lines. So we check how many lines are passing through a surface. That surface is virtual. It is not real. Virtual means imaginary. We can imagine a surface from where the field lines is passing. Now there is a close relationship between flux and number of field lines passing through any surface. So whenever we are interested in calculation of flux, we assume a virtual surface in an electric field, and then number of electric field lines passing through a surface is called electric flux. So electric flux is denoted by number of field lines passing through a virtual surface. So as we have discussed that flux is number of field lines passing through a given surface. and this flux is equal to number of field lines per unit area. Suppose 10 field lines are passing, then you can say per in a square centimeter, you can say 10 per lines per square centimeter. We can also represent in terms of number of field lines passing through area of interest, either a unit area or area of interest. The flux can be calculated. As we have defined the flux, number of field lines passing through a surface, units of virtual surface. Now it depends on several parameters. Can you see the difference between these two figures? In the previous figure, only three lines are shown, whereas on the second right hand side figure, six arrows are shown. If I am assuming then these circles that we have shown are basically are the virtual surface we have chosen, and these arrows representing electric field lines, then more lines are passing through the second figure than the first, and the flux is proportional to density of flow. In the same virtual surface, more lines are passing through second. So in the same area, the flux is more for the second than first. Here the flux is more. Now see again these two virtual surface we have chosen. Can you check the difference between these two virtual surfaces? Yes, you can see easily the direction of field lines is same in both. However, the virtual surface have different orientation. In the left hand side, you are observing the field lines and the virtual surface is having other angle than 90. Whereas on the right hand side figure, both are perpendicular to each other, the surface and the virtual lines, the field lines. However, it is sometimes difficult to check the direction, and that is why the flux, the surface is denoted by normal vectors. So, but there has been some angular change, and we observed that the boundary faces the direction of flow, and due to this, these two have different flux. See this figure. Can you judge the changes here? Yes, this time we have changed the area of this ring. The right hand side have more area than the left hand side. This is the difference between this figure and the first figure is in the first figure only field lines are changing, and here this area of surface is also changing. If this area is more, then more field lines may be passed through. So this is just to remind you that this also depends on area. More area means more field lines may pass. So we have shown here three categories, three conditions. One is area, second is number of field lines may be more with the same area may be more, the second, and the third thing is the direction. If you change the chosen surface direction with reference to field lines. So all three things affects the flux. The electric flux is defined as E into A. If you have chosen area A to pass the field lines, then this is EA. Here is the applied electric field and A is the area. This is shown in the figure also on right hand side. An area, a rectangle area chosen and shown in the figure, and electric fields are passing through this. We must rewind this whenever which we have chosen area element, then this area is always represented by normal. So the area vector is always perpendicular to this chosen surface. So here it's shown by A, and E is the electric field. So the flux is given as EA. In electric flux, as we have discussed in the previous slide, surface area chosen is very important. If surface area chosen is not perpendicular to electric field, we have to slightly change our definition. If it is perpendicular to electric field, then it is always equal to EA. But if it is not, then we have to consider the angle also. As shown in the figure, the electric field is passing, and so the first surface is shown as a perpendicular, which is perpendicular to the passage of current. On the other hand, the another one is having some angle phi, making some angle phi. So in this case, the area vector which is perpendicular to area is different than the first, and this area vector is making some angle phi with the new area vector. So the phi e or the flux can be written as Ea cos phi. So check this. In the previous case, if they both are perpendicular, we can take Ea, but if it is, the general formula can be calculated. Phi e is equal to Ea cos phi. Here phi is the angle between the field and the unit vector which is perpendicular to field. So this formula is more general than previous one. So we can see that the relationship between the flux and the electric field and the area vector is just dot product of two vectors. Phi is just a dot product of two vectors, and dot product of two vectors give us scalar product. We know this. Phi e is equal to E dot A. However, this can also be done as E dot an, where n is the unit vector perpendicular to surface. The direction of a unit vector for an open surface is always ambiguous. See here, if E is the field which is passing and shown by blue lines, and A is the area vector chosen, then the direction of unit vector is perpendicular to outer is shown here. Similarly, if you want to check the unit vector on the right hand side, is given by n cap again. It is always pointed outward direction. For a closed surface, the unit vector is taken as being pointed outward. Here in the figure, we have shown a spherical surface. At all points on this spherical surface, the unit vector is in outward direction. Now see another figure. The electric field line entering through a closed random surface, and same field lines which are entering from one side are leaving from the other side. So this concept can also be used to calculate flux. Here, flux lines enter the surface. The surface normal and electric field lines are anti-parallel. The meaning is where the lines are entering from this side, this should be the direction the lines are entering. However, the surface will be in this direction. Whenever we study on the boundaries, because as we have discussed, the surface always outward direction, and here the electric field is in inward direction. However, the condition is entirely different on outer side. On outer side, this is, I am showing you perpendicular direction and outward direction, and similarly these two are parallel as per principle. Of course, the flux line exit surface, they are parallel. Emitting side is parallel and anti side is anti-parallel. Now try to see this figure and analyze the thing. Whether there is a difference in the net flux through the cube between the two situations or not. In this case, before answering this, just think about here we have two cubes, and in this two cube N1, N2, N3, N4 and 5 and 6 are the normals of these cube surfaces. Yes, the cube surface have 6 surface cube have. This cube has 6 surface, and each surface is flat, so the normal direction is same. Is over all the for each surface is same, and we have 6 surfaces. Now we have changed the condition of we have changed the direction of passage of these two. In first it is moving in different orientation, the second it is in different. In the first all are normal, but in the second it is making some angle. In this case there will be no difference in the flux, because how it looks that it is having some angle, it is not, but as a whole you are talking flux through this cube. So the flux contains the same charge, and using Gauss law you must know the charge is same, then the flux will be same. It doesn't depend on other things. Total flux. The equation we have for flux is fine for simple situations. The electric field is uniform and surface area is spherical. What happens when either one or the other or both is not true? It means, suppose what happens when the electric field is not uniform, number one, and the surface area is not plane. Yes, we have many examples in day-to-day life where electric field is non-uniform. At the same time, the surface area is not needs to be in spheric flat form. It may have different shapes. Again, try to see the things. Here I have shown three figures. In first figure, the field line is moving in x direction and your surface in y direction. If the surface is in y direction, then again the perpendicular to this is considered as normal, and the normal gives you area vector. So the area vector and the electric field line both are in same direction. And the answer will be maximum flux. But if you just tilt this area with some angle theta, then the flux will be different or less. And finally, here the electric field and area unit vector is perpendicular. So there will be no flux passing through this. What I want to convey you here, the area is same, field lines are same, but flux is different, which is based on area and uh, flux area and field directions. In the case, we have talked about discrete charges, but suppose we have large number of charges and we want to calculate flux, then we must break the surface area into small pieces and then calculate the flux on each face and finally sum them. In the limit of infinitesimal area, it can be represented in terms of integral. Because summation has own limitations, you can do this also, then first calculate to first charge and then integrate it and finally give the answer. But if we can divide the area into different small sections, small pieces, and we know the electric field on each small pieces, then it can be calculated. Flux can be calculated. Thanks. It is advisable to do some numerical problems using our recommended textbook or some other books. You can also perform problems by internet and can ask queries. Thank you.